have to get my microphone going here. So it's another week, another Tuesday. And I just want to make sure that, okay, so the recording I think is continuing to happen right now as we speak. That's kind of a good sign. Okay, very, very good. So last week, I guess on Thursday, we began to code our so-called VESP 1.0. And you know, we wrote some of the early part of the code, if you like, and we wanted to get on with the rest of it. I guess more students will be coming in, so I'm going to delay my wordy remarks and actual lecture material to maybe 2 minutes from now. I just want to have everybody to come in. Jasser just signed up there, and so is Era has. Good to see you, everybody. And then I see Ekta Kamali. I had a friend whose name was Kamal Abdali. Your last name is Kamali, and his first name was Kamal. The last name was Abdali. That means a smart person. Abdali, I guess. Abdal is a very common word in, I think, Eastern cultures. Somebody who's actually developed, mature, knowledgeable, lots of positive things come with Abdali. Learned, I guess, in the English, Old English. Anyway, Jasser, you're okay. You look good to me. All right. There's a lot of light coming from behind here. Yeah, you look pretty nice, and you know you have a nice setup there. Is this a dorm?
Oh no, this is my home office.
Yeah, where you live. Okay, in your home office. Yeah. It looked for a minute, for a second, that you actually were one of the few students, brave students, who decided to storm it out on campus. Okay, or weather it rather. Okay. All right. So good to see you, everybody. Good to see you, Jasser. Let me just get to class. What that means is I'm going to have to bring my 350 material here, and I also have to do a couple of other things. I have to share my screen. I don't know if I can do anything about this particular thing behind me, but my lights is on. So, but anyway, let me just go ahead and share what I can share, which will be this guy here, and then I have to do this. There's screen sharing right there. And there you see it. So what we're going to do today, we will complete this exercise, which was this program that we began to write, and at the end of which we will then switch to another machine, which will be VESP 2.0. Okay. And this machine, maybe I should move myself a little bit. I'm just a little bit afraid of my loots being butchered here. If I do this maybe, but then I can't really, I can pretty much make that go away. Well, I don't know. I'll let it be this way. Okay, because it's straight across, right? I'm looking straight in front of this computer's right there. Maybe I just cover this a little bit. It's just like, you know, technology isn't that advanced after all. Okay, so we are now good to go. And I just want to get back to our lecture notes here. So if you remember what we did, what we were doing, we just wanted to do this simple sum, which was to, you know, like to take a bunch of numbers which we stored in locations A through 13, all hexadecimal. So there are 10 numbers in there. 13 is 19. A is 10. Between 19 and 10, there are exactly 10 numbers if you include, you know, one of the upper or the lower bounds in there. Okay, so now we got those 10 numbers in there and we put them in there. And then, of course, we had two other things that were going for us. And one of them was the so-called the sum location. And the more critical one of those two was the index register, which we didn't have, but we created one by simply allocating location number 2 to this thing, which we call maybe virtual index register, right? So what is a virtual index register? It's something that we create ourselves, and now we want to use it to index through a set of locations in memory. That's our goal. And so just to refresh everybody's, and again, I'm going to have to say this is our lecture number 7. We are actually going into, I guess, is it lecture 7? Yeah. So this will be our, I guess, 4th week then. All right. Time really flies. But let me just write this first. Okay. And, this is, what is it, February 16 already? Time does fly, as indeed it does. So let me just, refresh what we're doing so I can continue here. Just let's go back and briefly look at what we did. Okay. So this is where our code began, if you look at it. And the first thing that we did, if you notice, we initialized the sum. And I've written those things, and you have this, at your disposal. I'll be basically saving these 2, I guess, weeks of lectures by the end of Thursday, and then sharing them also on Elms, just like I've done the other, I guess, 2 weeks of lecturing. So we're going to do these 2 weeks at a time. So by Thursday, I'll come to the end of the second 2 weeks. That will then give me the ability to actually pack all the stuff and then put them on Elms for you guys. So we initialize a bunch of things here, as you can see, initialize the sum, and then we initialize I, and we initialize it actually to where it points to. The first element, which happens to be in location 10, that's all hexadecimal. Everything I write down here is hexadecimal. And then after that, we begin to place our numbers from, like, location A. This is location A. We started to load into these locations like number 1, number 2, number 3, number 4, etc. We keep putting them in there. Okay, as we do, of course, we also count, what locations we get to by just simply moving more things inside. This is our sort of like program, which is now residing in those locations. So we continue doing this all the way up to here. The last place being, as I said, location 13. And into that location, we put number 10, which is A. So effectively, if we do this right, since we cleared the sum, and we add these numbers from 1 up to 10, we will get basically 10 times 11 divided by 2. That should be 55. And in hexadecimal, that will be 37. So with that in mind, now let's see what else we have to do, because we've already put the numbers in there. We initialize the 2 things that are critical. And now we're going to go ahead and do the rest of the work. So one of the things we have to do is, this is like a loop. We're going to go into a loop right now. And in this loop, we're going to check to see if, before we do anything else in this loop, we will check to see if in fact we reach the end of the array, right? Right now, we initialize it to location A. We know that we're not at the end of it, but we want to insert some piece of code in here that will give us the ability to actually check to see if this index register, which is like location 2, as we will be incrementing it along the way as we enter this loop, will not exceed 13. If it does exceed 13, if it becomes 14, that means we have actually gone past the last element of the array. We're assuming that there are only 10 elements in our list. That's how we created them. So that's what I was trying to do here. I just said copy I into the accumulator, which is like how you do this. When you want to move something, a lot of students struggle with this, and I understand that. Like 3 versus 2, whether you use 2 or 3 here. When you want to copy something from a location, you put the 3 in there. When you want to load a location with a number, with a constant, you want to put a 2 in there. This is like to put a number in there, which we are now putting in. And this is like we're copying. That's what the word copy means. With a 3, we're copying. With a 2, we are actually loading. I call that copy command the move command, even though we don't literally move things. We don't erase things. We simply get them, from one location to another, but we retain the original value in its original location. So you can see that I've come up to this place, and the only thing I've done so far is to just copy I into, I guess, location 0, and then copy 14 into location 1. And I want to perform a subtraction at this point in time. So how do I do this? How do I actually subtract numbers from one another? I mean, I'm just checking to see if this thing has become 14. So it doesn't matter if I subtract B from A or A from B. I would just go ahead and complement whatever I loaded into A, added to 14, which is now sitting in location B, and then add one more to it so that I'm doing a 2's complement subtraction. As you all remember, that's how you did 2's complement subtraction, right? Unless you've taken this class 244, long time ago, you know how you subtract numbers into 2's complement. You complement the so-called, I guess, the minuend from the subtrahend, the minuend complemented and added to the subtrahend, and then you add 1 to that thing that you just added. That will give you the 2's complement difference of the two numbers. So that's what we're going to do.
Professor,
Yeah,
just to clarify, so 3, when we're doing the move, we're copying the value that was in I to the accumulator, which is A, and 2, we're
right.
just loading the location 14 to the B accumulator or the Q accumulator.
Exactly. So this way, by doing so, we have a constant in one of the locations, which is location 1. And the reason we brought them in here because we couldn't add them, in other places. You remember 0 and 1 are our very prized locations. Those are the places where we actually have our accumulator and the co-accumulator. Anything that we do in the way of addition, complement, those are the two useful things that we have, other than the move and the copy commands, that load commands we have here. I think they have to be done with respect to those two places. There's no other place where we could do this. Everything that you want to add, complement, you have to bring them into these two locations. This is a very simple machine, as we already know. Okay.
Professor,
Yep.
I didn't quite understand when you explained the difference between copy and load, because I'm under the impression that they both take the value from another location and put it in your destination location without erasing the previous value in the previous location, right? So then
Yeah,
what
but
is
what's
the
the difference then between the two?
That was my question. That's what I'm confused about.
Well, I mean, we created these two instructions to make them different, right? Do you think that I'll be fool enough to actually have the same thing done twice?
No, but
Okay, you want to know. All right, I'll explain. That's what, that's why I invited, I mentioned what I mentioned, which is I think some students get trapped on this one. So when we, describe these instructions, and you can go back and I can, move things back, but I don't want to do that. The difference between the two was that load will actually put a constant, a value to a location. Right? Just think about that for a second. Load is an instruction that's going to just put a value into a location. So the buzzwords are location and value. Those are two things that you have to keep in mind. Whereas the move command takes a value from another location, from some location, and puts it into a location. So in one, I take a value and put it into a location, Tassin. And in the other, I take a value from a location and put it into a location.
so you get to specify where you're loading it from. Is that or move
The
choosing
move
it?
is going to have to give me an address where I find my operand.
I see.
Whereas load doesn't give me an address. Load actually gives me the value itself.
I see. I see.
It's like the idea of a pointer, basically. And if you have indirection, as we learn in some other, technology that I'm going to share with you, code appeal or code mill, we will have indirection where you will have handles like in C, as opposed to pointers. Basically a pointer to a pointer. These things, you probably get these in the end. But this is the difference. Did you get that, Tassin?
I did. Thank you, Professor.
You're most welcome. Anytime.
Can I ask a quick question?
Yeah, sure.
So we have two lines. Well, like the first one says copy or load to where, and then the second one is like whatever value you're copying into A. For example, like right now you're copying 3 is copied to A, and you're copying 2 into A. Is that?
No,
is that what
I'm not copying 2 into A. I'm copying what is in 2, location 2 into A. The other one is, yes, I'm copying 14 into 1. One
think
copies
what-
14 into 1, and the other one copies what is in location 2 into 0, location 0. It's hard to get this, I know. And when you're doing it the first time,
So the
I sympathize with you. Yeah.
So the copy is that you copy whatever that it's inside location 2 into A, and then the load is you're loading literally the number 14 into.
Yes, there you go, Victor. You got it. Keep it that way. Just, you know, you got this now. Just keep it that way. Everybody keep it that way, please. All right, so we got this far, and I haven't done anything except to load these numbers. And I was just explaining to you, you know, that we have to do 2's complement addition to get a subtraction. My goal is to subtract what happens to be now in location 0, which is A, from what is actually in location B, which happens to be 14. And as I said, it doesn't matter if I actually subtract 14 from accumulator or accumulator from 14. So I'm going to go ahead and I cannot complement B. I can only complement A. I'm going to go ahead and complement basically A. So how do I complement A? Let me just keep track of things here. So we're basically now, let me just copy these if I could do that. There's a way to do this thing gently if I could really do it. All right, let's see if I can just do this. There you go. So writing this again, let's just move on to lecture number 7. All right, there we go. So we just copied it down here. I want to be able to, you know, yeah, you can even reduce the size of it. So you know where we are now. So let me continue. Let me just actually press this and that goes away. And I'll just erase this little piece here, this little piece. Okay. There we go. So now what comes after 3B? Of course, it's 3C. So I'm going to write now the rest of the code. Okay. 0x. This is the new thing. We're just doing this after this. Okay. 0, 3C. That's the location. And now I want to do a complement, which is basically this instruction. Complement A, accumulator, that is. Okay. And then I want to add to it what is in B, which is 0, 0, 0, 0. That's how you add. Add. Okay. Basically add, you know, add. Let's just leave it that way. And then 0, x, 0, 3e. Now I want to add one more. And how do I do this? Now that I already actually added 14 into A, I can erase it, destroy it. So what I'm going to do, I'm going to put a 1 into B. This is the way you do it. Okay. Load 1 into B. That is the co-accumulator. That's what it is. Okay, now I have to do one more addition. This time will have to happen in the next location, which is actually 0, 4, 0. So I'm going to go ahead and put that in, which is 0, 0, 0, 0. Add. So what did I do effectively, Jasser?
You want to add the B accumulator to the A accumulator. That's the first step with the 0, 4, 0 that you had with the 4 zeros. And now the other step would be
No,
Um,
I mean, I'm asking for like location 3C through 3D. That's
Oh.
all the way 4440, that is.
40. Yeah.
What is 100 doing?
100 doing is complement.
Complementing A, right?
A. Yes. What's an A?
And what do I do after that?
You add whatever. We add the co-accumulator and the A accumulator and store in the A accumulator, which is 0000.
I'm
This is
not,
the
I'm not saving anything in there. I'm not looking at 3D. That's just an add instruction.
So you're adding, and the add
The
is
result goes into the A, of course.
Yeah.
Yeah, sure. I'm adding and result goes to A, yes. What happens after that?
and then you load one into B.
Right. Wouldn't I destroy 14 if I did that?
Yeah, because you're changing the 14 to 1.
Is it okay?
Yeah, I assume it's okay because you already use it in the A accumulator. So
There you
that,
go. I was looking for the expression. You already used it. I can destroy it now.
yeah, you don't need any.
This goes to show how you share spaces. Like you're on a bus, you take a seat and then there comes a bus stop. You just, get off the bus. What happens? Someone else boards the bus, takes that seat. You're gone. You don't need that seat. You're not going to take the seat with you, would you? No. So this is shared.
Yeah, so we usually treat the B accumulator as a temporary value to store stuff in A. Does that work that way?
Both places are kind of temps for us. We cannot keep things in there and then hope to have them there. Just like when you leave that bus, you kiss goodbye to that chair. You may never see it again. Okay, you get the idea? It's like, you use it and you move on. Someone else takes over. Okay, so this is the idea. Now we put the 1 in there. We add the 2, which is that last instruction. We got in A the difference of 14 and what we copied into A in the first place, which was our index pointer or register, right? We took it from location 2 and then put it into the accumulator. Now we subtracted this thing from 14 to see if we got to location 14. If this produces a 0, we know that we got to 14. And therefore, we got to bail out of here. We got to check out of here. How do we do it? We use one of those other instructions. We got to jump out of this place. We have no business of being in this loop. So let's just go ahead and do that. So what is the jump if 0 command? What is the opcode for that? 5, isn't it? Or is it 4?
It's 5.
It's 5. 4 is force jump and 5 is jump if 0. So our next place is, which is 0. This is not 6, by the way. This is just 0 here.
Professor.
Yeah.
One thing is not so clear to me. If you scroll up a little bit.
Okay.
So from the last class, we had 14. We loaded 14 into B. Now, when did we move B into A?
We're never moving B into A. We're adding the complement of A to B.
Oh, so you okay. So that add is already okay.
All right. Very good. Let's go on a little bit. Just get some speed here. So 0x041 is going to be our so-called 5. And I want to go to a place which we don't know where yet. So I'm going to put here x, x, x. I don't know where I will be going out. In fact, I know where I'm going to go, but I don't know the location of that instruction. I just should say here, go to halt. But I don't know where that halt instruction will show up. That's why I put the XXX in there. Okay, I don't know what location I'll put the halt. I could actually create a location and then write halt in there. That's fine. But I want to sort of keep the program order as we go forward. Okay. So now this is the very critical part here, which I think you have to pay extra attention. I may have to tell you this about 4 times. Okay. Now we're going to use, we don't have a lot of capability in this computer, but we want to be able to do this indexing. I think I've led you to believe that we could do this up until now, right? You never question, this because I've done this class so many times. Obviously, there's no, unexplored territory for me here at this point in time. And I know that, we're going to a place with this. So you probably have that faith in my explanation of things here. But let's still think about what limited capabilities we have, and we have to overcome them. We got this move instruction, and we got the load instruction. Load instruction is almost no help. In fact, no help, because load just values a constant. What we want to do at this point in time, realizing that we haven't gotten to 14, we're somewhere in between A and 14, we got to pull a number from this so-called array of 10 values and put it into one of the two registers, okay? And that is, we're going to have to really do something very clever to do this, because our move instruction doesn't do that per se. Our address is stuck in IX, or the index register, but our move instruction wants its address right next to it, right? Isn't that true? When I have a move instruction, I put the opcode 3 and then write a destination address. Right below that, I must write an address from where I'm going to grab whatever I want to grab. But the address that I want to grab the things from happens to be sitting in location IX. So I'm going to be in some jeopardy to be able to do this. If there's any hope to do this problem, that will be by way of a move instruction. And that instruction needs its source address right next to it. But that address is sitting in IX. So you can see now that I got to move that from IX into that place where the second location in my move instruction happens to be sitting. So this is called a self-modifying code, and it requires a pair of move instructions. One of them is called the auxiliary move. The other one is the real move. Okay, let me explain this. Okay. So at this point, I will write these, bits and pieces of code, and I will explain things to you along the way. So here, at this point, let me just actually do one more thing and then go to this. So first we have to bring the sum into one of the two places. Let's put it into A, right? Because we're going to add this to the sum, running sum. So I'm just going to go copy that first. 0x042. How do I copy this sum? That's not a big deal. I put it 3 and I bring it into 0, 0, 0. And where was my sum? Anybody? What location?
Location 3.
All right, there we go. So this brings the sum into A. Now the tricky part. I want to bring the other thing, which is the A of I, that is the array of I. I is a number between 10 and 13. Okay, I know that I didn't go to this place to halt. I'm inside the loop now. Okay, so here we need two moves. Okay, to move, let's call it, array I into B, we need two move instructions. Back to back. The first one is called the auxiliary move. The second one is called the real move. All right, I think something's open on my computer. It's just getting a lot of noise heating up. Okay. Maybe I'll just quit my mail here. Okay. All right. So now we settled on this. By the way, think about any of the other instructions, they will be of no help. We could possibly play with the jump instructions, but it's going to be a mess. Of course, we could always do this linearly without writing a loop, but that will be cheating because what if I don't want to add some 10 numbers, but 1 million numbers? Are you going to write a linear code where you make all these additions, like one at a time? It's not possible. Okay, you want to write a loop. So let's just keep track of what locations we're in. Now we are in location 1444 now. See, just pay attention to that, please. Our next location will be location 044. So let's just write that down here. 0x 044. Okay, one more time. That's where we are. I didn't make a mistake in just adding these numbers. Yep. All right, there we are. We got two moves, I said. One is the auxiliary move. I'm going to write that down. 3, some address, which I'm going to determine in just a second. Okay. And here I'm going to write 0, 0, 0, 2. Okay, and this is in location 0x 045. Auxiliary move. Okay. All right, so what is why? It's not like I'm asking why, but it's like 3 Y's in a row. Which actually can be interpreted as like emphasizing why did I write the 3 Y's. And the next location is 0x 046, 0x 047. And this instruction is going to have 3001. And I'm going to write maybe, in here, U. Okay, so let's look at these two move instructions. It's clear that I have two move instructions, right? I have a move here and a move there. Now you notice that the destination of the second move is where? Where is it going to go? Into B. So I'm going to take something into B. Where should it come from?
U.
Right, and what should I make U? What happens to be in? 0, 0, 0, 2. So that Y should be this address. 0, 4, 7. And what about these UUUs? Doesn't matter what you write in them. You're going to overwrite them. You're going to write over them. So you can write anything in here. And, and the best thing to write would be 0, 0, 0. These will be destroyed. By the auxiliary move. So anything you write is good. Okay. So this is it. Now we managed to copy what happens to be in our array in the current running index position straight into B. All right, everybody, you got this under your belt fairly well secured in there, right? You understood this, correct, Jasser?
I understood that Y gets the location 047, but I didn't understand what happens with you. You said it will be destroyed, so it doesn't really
Yeah,
matter.
because I'm copying. If you look at, what is, if I write 047 here, what will happen to location 047, which is here?
So we're not really using it. It's going to be 002.
Not 002. It'll be what happens to be in location 2, which is our index value. I'm not putting 2 in there. I'm putting into it what 2 points to, the index pointer, right? And that's our running variable, right? Running index, isn't it? So I'm putting the index value, if you like, into the position of these 4 U's. By the time I get to that second move, I have my address squarely looking at the ith element of my array. And I want to copy it now into location B. That's what these 2 moves together do.
So is the point of the auxiliary move to basically determine the source address for the main move?
It determines the source address for the main move, yes.
Okay, thanks.
And we need, with these 2 move instructions now, with these 2 moves, we are able actually to do what we wanted to do, which we couldn't do any other way. Okay. Barring writing a linear code or some really juggling with some jump instruction where you would have to make this spiraling down a loop, which is maybe a way to do it, but not very clean, not very neat. All right, so now we are looking at 2 numbers, one of which happens to be in A, and you know what we did with A, which was to copy sum into A. And we put the running value or the current array value, okay? So these 2 instructions together I just write this way. I want to. Together, copy array I into B, that is the co-accumulator. Okay, you got that there. All right, well, there's not much else to do. Once we get these copied, placed into the right places, what else should I do at the next location, which is 0x048? I must now add the 2 numbers together, correct? Right, Tasin?
Yeah, sounds right to me.
Okay, let's go ahead and do that. What instruction would that be? You tell me.
To copy the 2 numbers to.
No, we copied them. We now want to add them.
Oh, so that would be zeros and then the location.
No location.
Oh,
right?
right, no location, because add always adds A
Yeah.
and B.
So we now added it to put this stuff into A. So at this point in time, accumulator is going to have sum plus array of I. Can we afford to leave it there?
Not for long.
Not for long. So what we need to do is to save it back to where it came from, the sum came from. So now we go push this back into the sum location. That means we have to do this. Move, always move. Then what location into which we're going to move this?
3.
3, great. And from where would it come?
Come from 0.
There we go. I think you're beginning to catch this. right? So this save the running sum back to sum. All right, you get this. Now we saved it. What else is left to do? Is there left to do? We must increment our
I.
I and then go back.
So
Okay.
we have to load I into the accumulator. And
There
then
you go. So now we're going to go ahead and load I, which will be, 0x. This is 0 4a, 0x, 0 4b. That means we're going to put into A what is in I, which is this location. Copy I into A, to the accumulator, that is. There are too many A's in here. All right, now that's 0 4x, 0 4c. Okay. And then load 1 into B, 0x, 0 4d, 2 0 0 1. And then we want to put 1 in there. 0x, 0 4e. Okay. That means here, load 1 into B, the co-accumulator. Okay, now we got the 1 in B and then the index in A. We want to add them up. 0x, 0 4f. Add the 2. Okay, so that adds the 2 together, but we cannot afford to leave it there. We have to copy it back into
the I.
0x, 0 5 0. Okay, and that means we have to copy it back into I. From A, 0x, 0 5 1. And now we have to jump back to where this all began, right? So 0x, 0 5 2 will be a jump command. And what's a force jump?
5xxx.
Yeah. So let me just say save I. And this is actually 4. It's a force jump. 4, maybe Z, Z, Z. Jump back to the loop. Okay, let's see where the loop is supposed to begin. Now the loop begins where we loaded I into, or loaded some, I guess, into A, and then AI into B. Or in fact, not even that, but we were checking to see if something became 14, remember, right? So let's go back and find that place. Where is that? Not there for sure. Okay. Not even there. There it is. That's where we copied I into A and 14 into B. And then we began to do this process. So where should we jump? What should Z be? Location 38. Yekta, you following this? Good. So we we just cross these out. 0, 3, 8. So what's our next location here? Our next location is 0x, 0, 5, 3. And what should I put in here? I'm done with my program. What should be the instruction to place here?
Oh,
Alt. That will be 7, 0, 0, 0. Now, that is the location that we should have jumped to when we were actually trying to figure out where to go up here. So now I can come up here and then replace these by 0, 5, 3. And everything has been specified in my code. Okay, so maybe we can now run this program. Okay, I discovered, by the way, the reason that my computer crashed, not crashed, but the Xcode crashed on, not that it didn't crash, but kept running, was because there's a bunch of, I don't know if anybody owns one of these new Macs, like this is Mac 2020. They have some programmable bar in the very back. And sometimes my fingers touch those programmable bars. So if you ever hear a sound when I am typing my program, that means that program is not going to run properly because that is entered into the computer and then the Xcode thinks that I type something in there, which is not a valid character. And it's going to mess everything up. I'll try to be very careful not to have this happen. But if it happened, don't worry because I actually have a backup copy of this program and I can always cut and paste that or in fact open that. As a matter of fact, I may even want to do that now at this point in time so that I can get some speed, all right? Instead of like typing this, it may be instructive to try to type it and maybe get that first sound and then give up on, entering the code on my computer and then maybe just, open this file, which I will do. You may, all right, so once you do, once you get this far, you notice that I haven't done anything with my computer. I didn't bring up my, compiler or anything. I just wrote the thing on a piece of paper, so to speak, like this looks like a piece of paper here. Now take all of this and then put all of this into the computer. Now, if you are, well-versed in typing things and, like thinking at the same time, then you can type this code as you're thinking and make changes. It's up to you. But the point is that, you want to create this and then make sure that, what you have created is good. And then you can go from there. So I will just switch myself to, like sharing my,
Um,
I'm going to, yeah,
Before we move, I just have one question.
yeah.
So now we initiate the code to go from to increment I and to go over the array. But how is it gonna keep on doing that in a loop? I just can't visualize it to go in a loop.
So what we did, if inside the loop, what we did was to actually load the sum into A. And then we, by way of these two auxiliary moves, we moved what happens to be in the array in the ith position into B. We've done those things, right? Here we did do them. There we are, like here, right there. These two instructions together copy array I into B. So those are there now. Okay, and then we added them, as you can see, location 48. And then we saved the running sum. So that took care of that, inside the loop, we managed this. Now, our next thing is to increment the index pointer and check to see if, in fact, we reach the end of the array, which is at the beginning. So once we increment the, like here, copy I into it and all that stuff, we are incrementing it by 1. So it's gone up by 1 now. Now we go back. This time we're not checking what we were checking before. It's a very clean-cut code. I mean, I don't think it gets any simpler than this.
So it just repeats itself over
Until it finds that it's actually equal to 14 and it just bails out.
Oh, okay. So that's what we did when we added the 14 in the beginning. So that makes
We
okay.
subtracted 14. Yeah, we subtracted actually A from 14. That the way we did it. You could have done it the other way around. You could have loaded 14 into A and the index into B and then done the subtraction, differently. Doesn't matter
Makes
because
sense.
we're looking to get a 0 out of it, basically.
Thank you.
I think in some of the solutions on the web and other places, I may have done this in reverse. That is to say, put the index on B and then 14 in A and then do the subtraction that way. It doesn't matter. All right. So what was I
Wait.
saying? Yeah. You're all set.
I was
then?
going to ask
Yeah. Who's that?
that this is Tassine.
The scene. Yeah.
So if we don't meet the condition, right? Like if the jump if 0 doesn't trigger, then is there like a line that jump? Is there like a jump command that forces us back to like the beginning of the evaluating what's inside the loop?
No, there's a jump command which we used here for like location 52.
Oh, so that takes us to the beginning of the loop.
Yeah, like
If
takes
we-
us back to 38, which is this location here,
Okay, I see.
right there.
I see. Thank you.
Yep, that's right at the beginning, 38. That's where we began to actually check to see if something was like the I was greater than 14 or equal to it. All right, any other question? Nobody corrected me when I wrote the February without the Y at the end. How did I do that? So unfair to February. Okay. It's one of the best months of the year. That's when, trees begin to have their buds sort of like signal them for spring. Have you ever grown any trees, like from a cutting? Do you have any trees in your backyard or front yard or on the street, wherever? Just
Yeah, we had them back home.
Huh?
We had peaches and apples, apple trees.
you do have some of those trees in your yard?
Yeah, but not here, back in Jordan.
Back in Jordan, yeah. So you can take a cutting from one of those trees and dip them in some water, maybe with some growth hormone or something, but you don't have to. And just keep it there for 2 weeks. You can actually do this, after class today. Keep it there for 2 weeks, and then you'll see that that cutting will actually begin to sort of change its look. It's going to have some little bumps on its skin. That means there's growth in there. And then you take it out and then put it in soil, in a pot maybe, and then it'll actually bloom. Next time I'll show you one of those that I've actually done when I get a chance to go downstairs and see how they're doing. I'm growing now apricot trees out of cuttings. February is the great month for that, by the way. That's why we just talked about February. It's really a great month. And in these times of pandemic, or pandemic, whichever way you want to say it, I'd say it's maybe, it goes to show that not just COVID can reproduce, but other things can reproduce as well. Okay. It just gives you a bit of a peaceful sort of mind. All right. So now that you've written this code, we just want to transfer this into an actual computer. And that means we have to type it, or we have to actually, have it in a file. On that, I want to tell you a couple of things now. The VEST 1.0 is like the bare bottom of, coding and machines. It doesn't even let you save your whatever you typed. So if you made a mistake, you're out of luck. You have to type it all over again. There is an edition of it, which is, I think, VEST 1.1, which gives you the ability to actually sort of like save it, or maybe load it from a file. And then from 2.0 onward, you can actually save whatever you create. And then you can play with it, by using a text file editor or something, and then you can go from that. So let me just be careful not to have my fingers touch the very back row of keys, which are actually digital keys. That means like keys that are programmable. That's what Apple decided to do. But they made the base of the computer too narrow. My fingers sometimes touch those keys. I actually disabled them, but even then, you may hear a sound. Because if I didn't disable them, I'll have a chaos on my computer screen. It'll jump from Safari to, Google or Chrome, and all my apps will be like, mishmashing in front of me. I don't know why a computer company could be so incompetent to make such a mistake. Maybe they didn't think of a person, with hands like mine. Okay. A little big, maybe. I don't know. But let me just get back to the work here. So I'm going to just share my screen. That means we're going to, I just go back to this guy here. I will share my computer screen, which I think I'm doing by doing this, right? And did I share it? No, it seems like it is still that one. Where did it go? Share. There you go. Now we have it. Okay. So I'm going to open my Xcode, which actually you can see what I did here. I've done this program before I came to class to make sure that, it kind of worked. You see that number 37, right? Which was what I, advertised earlier. What location is that in, Jasser?
Location 003.
Right, so that's where it's supposed to be. So I ran this code and I ended up basically getting this. But let me tell you what the code is, like. Here's the code. And I actually looked at the execution of the code here. And I'm trying to be ever so careful not to touch those keys here, there, at the back. So this is like how the code ran. And here's the program. So what I'd like you to do is to take a look at this code and see if this is any different than the one you have in front of you. Okay. So let's just carefully look at this code. And I can type this in. You can type it in. The way you type it, by the way, I just saved it from a file because I'm actually, if you notice, I'm running 2.0. And this is the only way I could actually save this in a text file. And then I typed this part way, something like to the middle, somewhere to the middle, and then I saved it. And then I kept adding more and more into it until I completed into it, an ordinary file, a text, straight ASCII file. Now, if your ASCII file has some special control characters that are not visible, then you may actually not be doing too well. You make sure that that's a straight plain ASCII. Like on Mac, you can actually make things plain ASCII, plain text, that is. If you do, then you won't have those spurious characters in there. But otherwise, if you're just copying it from, Microsoft Word or PowerPoint or some other app, it may leave some spurious characters that may not be visible to you, and then your code may not execute the right way. Anyway, so let's go over this. Now, I think, I don't know if I can make this any larger. There's a way to make this larger, but I don't want to waste a lot of time on this. What is that? There you go, maybe here. They keep changing this all the time. I can't really tell exactly what is doing what. They may have just, I don't know. There it is, yeah. So let's go to console. They put it into a place called themes, incredibly. Where is the console? Yeah, this is default. Let's see. Okay. There it is. I just finally figured it out. Okay, so that everything here, I want to see if I can actually pick him up like this and give it a size. Like maybe like this big. There you go. Figured it out somehow. All right, so you can see this, bigger this time. Let me just go to the very beginning. We could technically type this, but I think at this point in time, I'm a little nervous about that back panel of keys right there. Okay, so that, let's just take a look. So the first two instructions, they start at location 20, by the way, you can see 2003. And then, you know, I put a 0 in there. That's a copy, that's a load. And I then initialize my index register by doing that. And then I start copying things. So let me go a little fast here, like, you know, 1, 2, 3, 4, etc. You can see what I'm doing there, all the way up to 13. There. All this stuff is like initialize everything. Okay, the next place is I'm going to copy the index register, as you can see, right? We've done that, did we not? Did we not? I copy now the index register's content into A, and I put 14 into B, right? What do? I complement A, and then I do add, and then I put 1 into B, and then I add. Where do I go? If in fact that's equal to 0, location 53. So far, everything matches it, you know, what I've done in my writing, okay? Now, if I didn't go, I have to do my addition. I talked about 2 auxiliary moves, correct? But before I guess I do that, I have to put the sum into A. Now I copy whatever sum contains into location 0, which is my accumulator. And then this is where those 2 magical moves are, auxiliary move and the actual move. You see that I am changing location 47 by moving what the index pointer contains, which is location 2. All right. And that second, you know, like location 47 has some zeros, it doesn't matter what it is. I'm going to change it. How do I change it? I'm going to move whatever I contains by way of this auxiliary move. I could comment this, I'll say auxiliary move, real move.
Professor.
Yeah.
For the real move, are you just are you copying what's in the location, what's in A into B?
Are you referring to the 2 moves I'm just explaining to you, Yekda?
The one you just highlighted.
Yeah. So that instruction is going to actually move what I points to into register B. Why is that? Because that 000 you see in location 47 will be written over by what? By the move instruction that precedes that real move. What does this move do? It takes what is in location 2, yes? It takes what's in location 2 and puts it into where?
47.
Yeah, so that means this is going to be destroyed. I'm going to write over it. I'm going to write whatever the I contains will go over into that space.
Okay.
So now with the next move, I'm going to take the stuff from where I points to and put it into B. And that was my purpose. My purpose was to grab the element of the array and put it into B so I can add it to the running sum, which is now in location A, because I just moved it there. Now that the 2 of them are there, my only other thing that must be done is add them up. The second 4 zeros is not destroyed. This is an add instruction. This is like, I could have written 20, like in a number in there. I could have written, 1,000 in there. I could have written 2,000, 2,035, 2021. I could have written 2021. It would not have mattered because I'm going to destroy it by the auxiliary move. That's why, I try to explain this. All right, so so you can see that I've done that. I've done the addition here. I save it back into where it came from, the sum, right? And after that, I
Professor?
have to, yep.
Just about the auxiliary move, what's stopping you from being able to just load the index directly into B?
Okay, who's that, by the way?
It's Gabe.
Hi, Gabe. Yeah, so let's see if I could just get your question one more time. What are you saying again?
Yeah, so when we're loading the index into B, we're doing in the auxiliary move and then the real move.
Tell me
Why?
tell me the location, so I know.
Okay, yeah. So I guess starting at location 0x044, why can't we just do the instruction 3001 and then 0,
What
0,
was the location?
0,
0048, you mean? What was location?
0x044? That's
Okay, up here, you mean, right there.
yeah. So why can't we just load the index directly into B?
Explain that to me, the question, because I'm just, I think, thinking about what you're saying, but maybe explain a little further. So what does
Okay,
that do?
yeah.
What does that instruction do?
Which one at 0004?
0044.
Yeah, that's going to load the contents at I into location 047.
Right. And your proposal is to change it to,
Yeah, so what I was thinking is why not change, so at 044 have it be 3001 and then at 045 have it be 0002.
okay, so what would you do if you did that? What would happen? Think about it.
Well,
What
I'm sure there.
what would go into like location one? Let's just do what you just said. Let's say I replace this by 3001, right?
Right,
And then I just leave it as like 0002.
right.
Okay, so what will happen? Whatever 2 contains will go into this place, which is
Right.
actually now B. Is that what you want to do? You want
Yes,
to copy
exactly.
the index value into B?
But wouldn't that just be copying
No.
whatever
Whatever is
B-
whatever is in location, whatever this points to, whatever this address, which is 002, 0002,
Right.
whatever is in there is going to get copied into now not 047, but 00.
Oh, I understand. Right, because it's like a double pointer,
Okay, there you go.
kind of. Okay, right. I understand. Thank you.
You're welcome. Okay. That's that's why I said I may have to explain this several times because it'll get you, because this is like it's not complicated just because it's so indirect in some ways. Okay. This is called, by the way, I didn't write it down, but self-modifying code. This modifies itself. It's actually a very powerful technique. If you want to protect your code from potential threats, you can play what smackers do. You can basically play their game against them. You can change your code dynamically so they will never know what you're doing. And they try to reverse engineer, or in fact, smash your code, stack smashing. Okay, I'll just get back to her in just a little bit. Anyway, so you can see what we've been doing. And once we finish, I guess, putting the incremented index value, which we've done here, like we just loaded that into location 0, index pointer, and put a 1 into B and add the 2 together, and then save it back into the IX, that is the index pointer, save it, and then we jump back to the beginning where all of this loop was going into action. And then, of course, if it didn't jump back, we would then halt. That will be 700, 000. Actually, this is a force jump. It would not be like we wouldn't jump. We will always jump. But this is where we come to exit the loop here, where it says 5053. That's how we get out of there. In other words, our point of exit is at this place, not at this place. We don't exit from here. This is a force jump. We always go back to the loop, right? So here's a loop. And right at the beginning of the loop, there's a condition to say, hey, go out of the loop, right? Here's the loop, right? We're looping. The back end of it is always saying, go back to the beginning. But that says, hey, let me check. All right, exit. We're exiting from the beginning, not from the end. That's how the loop is. All right, so let's run this code one more time. Slowly. You assume that I've done this. right? Let me just go back, and then maybe it says type. If I could bring this back up a little bit. There it is. So it says, enter a program. I'm going to say 0. That's what happens when you, let me just open this from beginning so that, stop this. Okay, and I'm going to run this again. All right. So just fresh run. Everything has been cleared out of there. So I'm going to do this. And it's asking for me to enter a number. Again, I want to be careful. Actually, I'm okay now because I saved my file. It's in there. So I'm going to say, where should I load the program, by the way? What location should it go?
0.
Where should the program be loaded?
We are loading it in MAR.
Location 20, right? That's where we put the first instruction. Remember, it was 0, 0, 2, 0. Right? It was location 0, 2, 0, wasn't it? At the very beginning on the left, like the locations I was just beginning to write at the very top of the code, correct, everybody?
Yeah, that's what it was.
Okay, 0, 2, 0. Maria, you got it. I put that. I didn't touch anything here, hopefully not. Okay, I want to read it from a file. Now you guys have to type it in. And hopefully you don't have a MacBook like I do, okay? You won't get exited like I get forced here once in a while. Okay, so here's 1 to read it from a file. And I know the file of the name of the file. It was actually, it's self. I just created this mod.vesp. Okay. It says enter 0 to continue or save. I just, I know the file is there. I don't have to save it. Okay, it says sort of like gives me the same program one more time. So now I can execute it, or I can step it. Let me just step it. Okay. I'll step it to see what happens. I'll just type 1. Okay, so what it did, it just did the first instruction, as you can see. Program counter is at 20. MAR is 20. IR is 2003. That's my first instruction, if you remember, right? And then it just says load is the instruction. And it's now at clock cycle 5, and it tells me what goes into where. Location 3 has become 0. What did I do? I clear the sum, right? Isn't that what I did? I cleared the sum. And that's what happens. Now I can step it again. This is the second instruction, which is another load instruction. This time it's 2002. And this time I'm actually putting into location 2 what is the first address. My, array is going to start at location 10. I'm just copying it in there, putting it into location, the index. Okay. So you can just keep doing this. I'm going to ultimately, say execute. You will see the result, but I'm just giving you this step option so you can always play with it. Okay. So let's see what happens after that. So this time, actually, we're now beginning to load the constant. So the A gets 1. Let's just do this a little bit quickly. B gets 2. C gets 3. D gets 4. I don't want to touch that, one of those buttons. You see, I'm just doing one instruction at a time. You see that, right? Basically just stepping through the program. It's very nice. It's, it's relaxing. It's like, it makes you feel good because it's running. If it doesn't run, you get nervous, and then, you start pressing all the keys on your computer, and that's not going to help you. Okay. Now you can see what's happening, right? And then now we did something here. Let's see, what was, this was a move command. I think we must have done all the, so we've actually, this was the last time we put our number in. That was the last entry. But after that, we're going to be testing now things like, which was like something has become 0 business. So we are actually having an instruction, which is going to be 300, which has a backend, which is going to copy things into the accumulator. So what we did, we successfully moved the initial value of the index register into A. So if I step it, it's going to do all the other things. It's going to copy 14 into B. Let's just go ahead and take a look at that. Right, 14 just went into B as we wanted to do. There it is. Now we have to do the complement, so that thing that you just looked at, A will be complemented, right? You can see that that's how the complement worked, right? Do you see that? That's the complement of, 2's complement of A in hexadecimal. B hasn't changed, so now I have to add them up. You can see now that it has become 9, right? And we want this to be actually equal to 0. It hasn't become, it was really 10, now it's become 9 if you want. But we have to add 1 to it, I guess. Let's see what happens. Oh, this has already been done. Location, we haven't done this, I'm sorry. Let me just go ahead and do it. So it became 10. It has become 10. And it is not really, we're not at the end of the loop yet, is basically what I'm saying. So it's not equal to 14. It's not, the difference will not be 0 is what I'm saying basically, right? We're gonna have to go a while for this to be 0. All right, so like to make the long story short, you can keep doing this. And it's gonna basically step through, and you can figure out it, what's happening every time. You're gonna get back to the loop, and I'm gonna basically say 0 because it's 4 to 6 already, and then see what happens. Okay, I'm gonna look for a maybe long trace. That doesn't matter what it is. All right, you can see that the program halted. You can see how many clock cycles we used, 942 clock cycles. It's peanuts. If you have a clock rate of 2.3 point something gigahertz, this is like 0 time. It did all of this in no time. What happened? We want to see exactly if it worked or not. So we're going to go and put some information. So I'm going to display the memory to see, what the locations have. Right, the last must be a halt instruction. Let's make sure that is. What instruction is this, Yekta?
Halt.
It's a halt. So we ended the program. The program, happily ended itself. All right, now let's take a look at the locations. So I'm going to put some, maybe some numbers here, like first location is the accumulator location. I want to view those now. Maybe I want to, look at all the way to like maybe location 1F or something, like before the program starts, all those locations. I'm just interested. Actually, 13 would be all we need. Let me just do that on 13. Okay, so I can look at those locations. Do you see that sum being equal to 37? 3 times 16 is equal to 48, plus 7 is equal to 55. And that's what we wanted to get when you added numbers from 1 up to 10. Okay, and what happened to our location 2, which is actually 14, the last time we visited there. And that's when we got the 0, and that's when we halted. And you can see that these locations were never used, but these locations contain our array. Do you notice, Yekta? That's what we had stored. We never touched them. They are still there. It's a very nice computer, simple, nothing complicated, but it gets you all the ideas of what a computer is supposed to do. Fetch, decode, execute, fetch, decode, execute. That's all it does. And you don't have to, like look at a humongous machine with 500 instructions and try to figure this out. All right, I think it's a day for you guys maybe, and for me as well, maybe not. I'm going to teach another class in about an hour and a half. And, I'm going to maybe relax a little bit with my lute here. It's always there on my left-hand side. I won't do this, don't worry about it. I'll do this only in most extreme situations. Usually do this, to myself or with myself alone. But once in a while, I'll just hold it, and then maybe if I am in the mood. And if, by the way, these are very unusual times. So if you play an instrument, bring it on. Okay. Once in a while, we can change the tune because we are going through some unusual times. Got to put a mask on. I'm just still waiting for my vaccination to come my direction,
That's very nice, Professor.
which is nice. What is nice? I'm sorry.
Playing music.
Oh
Offering
yeah.
us
Do you play something, Ekta?
I mean, not professionally.
Well, nobody bad. Do you think I'm playing professionally? No.
Yeah.
What
Um,
what do you play?
I took piano and guitar back in high school, but that's
Oh,
it.
great. Yeah, my daughters went when they went to Roosevelt, and before then, in fact, they were going to University Park here in Maryland Elementary, and then they learned how to play the piano. It was very smooth, soothing. I used to go and watch them once in a while um, as they perform. They actually had some competition. Yeah, piano is wonderful. And guitar, I have a guitar. I don't really know how to play it. I just bought this. It's a left-handed guitar. I'm left-handed. I do play a few things, but not like people play the guitar. Like with all the rhythms and other things. I don't play it that way. I just play one string at a time. I still make some sounds that I like sometimes, not always, but I just never bring myself to this point of like figuring out where these four fingers go now. Next.
It's difficult to keep in track of which strings you're trying to make sound of, and then which strings.
I know there are these chords that you have to figure out. Okay, here's a chord, here's another chord, and then transition between them. There's one chord that you have to go all the way down, come back up. It's just not my cup of tea.
It's a lot of practice to be used to the.
A lot of practice, yeah, and not something that I just easily do. We're down to 17 students. We actually scared a bunch of students away, so let's stop this. Okay.
Professor, have a wonderful day.
You too, everybody, and you too also. I'll talk to you guys on Thursday. All right, take it easy.
Thank you, Professor. Bye bye.
Bye-bye.
Professor,
Maria?
I have a question,
Yeah, sure.
and it's something that I feel like should have been or was covered like in one of the first lessons, but
Yeah.
I somehow skimmed over it.
What is it?
So it's when dealing with IR.
Right. The
So like
instruction.
if you have the instruction like mar equals IR, and then you have a bracket. It
Let me see if
says
I can bring you back to, do you want me to go back to lecture notes?
it doesn't matter. I have in my notes, this particular one was from lecture 4 on February 4th. It was a Thursday.
Okay. Maybe I could just, just so that I know what you're asking. If I can do it. I wish there was some way of, let's see, lecture 4.
Yeah.
Okay, and then where are we in lecture 4? Like first page, next page?
I want to say it was at the beginning
Okay, I'm looking at some, flip-flops and stuff. D6, Q6, D7, Q7.
Yeah, so we're on Q7 or Q6 to Q8.
All right, so what is your question then?
So you have your mar equals IR, and then there's a bracket with 3:15.
Yeah, 3, yeah, that's right. Mhm.
What is that 3 and what's that 15 again?
Okay, so those are the bits of this, like we set aside the leftmost 3 bits as our opcode, right? When you say 000 in binary, that means it's an add. And if it's 001, it's a complement, and 10, it's a load, 011 is a move, etc. Those are 3 bits. So when we first defined the machine, I think we might have just created a table on an earlier page, but it doesn't matter. Somewhere in there, I must have written a table of At the very beginning, I guess I must have done that. I'm just looking at, yeah, so this is lecture number maybe 1. Let's see, what lecture is this? Yeah, it must be the first lecture, I think, very first lecture. Lecture 2. So in lecture 2, about 4 or 5 pages down, you can see that, I have an opcode sort of situation there, like, 000, 001, and then 010. And then to the right, I write these, operations like A equals A plus B, A equals complement of A, load, move, etc. So those are the codes that actually have to be placed into the leftmost 3 bits. And when I'm indexing this IR, I want to grab the address, which is now going to be located in bit positions 3 through 15, because 0, 1, and 2 would be the opcode bits, right?
Okay.
Yeah, that makes sense, right?
So you're grabbing the address. Let me write
Right,
that down.
because I have to get the address in that sort of situation that I think that you're like referring to, like, I'm just glad, yeah, that's at that point in time, I must be doing, either I guess what instruction? It's a move instruction, it seems. I'm doing a move. And so I have to grab an address from, I think, that address in the instruction register, I think, is the one into which I'm going to push. That's the destination address. I'm just basically conditioning my MAR to basically push stuff into, RAM or the core.
Okay, so that is the location of the address of where they're on in the bits.
Yeah, I'm going to sort of push something into a location that is, the destination address, so to speak.
Okay.
So that's why I'm doing that copying. My address is partly contained in the IR register. There are 2 parts in this instruction. I guess this is a move instruction. The second 16-bit word as a whole is an address where my source operand is located, whereas the first 16 bits put the 3 bits away. On the left is the place where I want to move that operand that is pointed by the second 16 bits in my instruction. Okay.
Okay.
Does that make sense to you?
Yeah, it does. Thank you.
All right. Was that it?
If you have time, I have one more question. It kind of has to do more with the homework.
Okay. Sure. Go ahead.
So in the homework, you're having us do something where we shift to the right and shift to the left. And last lecture, you went over this a little bit, but mathematically, how is that, or am I thinking too far into it? How is that being done?
So the left shift is like, you get it. You just picture a bunch of bits, and maybe I can write this down. Maybe I can just.
So like what I'm asking, so like for the add, you would write to, let's say the right of it, you would do A plus B would equal A for your add. When you shift to the left or to the right, what do you write? Like I understand what's happening.
Okay, let me just get the question first of all. So let's say we want to do like shift left, for example, right? Do you see that?
Okay.
You don't see that because I have to get back to my share.
Yeah, I can't see what you have.
No, you cannot see it right now, but I think in just a second you'll see it.
Yes.
Yeah, there we go. Okay, now you'll see this. Okay, so shift left, right? That's what you're asking for, or shift right? It doesn't matter, one or the other, right?
Right.
So let's say I want to shift left A, for example. Like A is a register, right, or something.
Right.
So here's A, and it's got a bunch of bits inside. Let's make it maybe for simplicity's sake, only 8 bits. So some number is here, 1, 0, 1, 1. I don't know if you're asking about this or something else. And those are the bits. Yeah, right?
Right.
Is this where the question is directed at?
So I can understand how you would then shift everything to the left.
Okay.
What I don't understand is, do you want us to mathematically show you what's happening? So like with the add instruction, you would have A equals A plus B because you're adding A and B together.
Yeah, right. Well, I think what I'm asking you, okay, so you know what this means. Okay, so what I'm asking you is, I guess it's in the data path or the ALU. How do you do this, right? Is that what the question is asking? I don't have the homework in front of me, but is it like asking you to do this somehow? Like, does it say implement? In other words, make it happen. Each and every instruction that's that's in there.
I don't think so. I was just wondering if there was a way to mathematically write it out what was actually happening.
You can write it mathematically, and but you can you can write it like this, right? I mean, this is like one way of writing it.
Okay. That is what I was looking for.
Okay, but this is you can write that. But to do this in a physical way, like with ENEE350 stuff, you probably have to use a multiplexer, for example.
Okay.
You have to have a bunch of multiplexers like this. Here's one, here's another. I don't know if the problem is asking. That's why I said I don't have the question in front of you. So you may have, for example, like, a bunch of bits here. If you're shifting 4 bits, you may have to put 4 of these. And then, you have to program these for your left shift. For example, left shift Y1 means that this will get out. And then, like when you're shifting, these are the 4 bits you have. And this guy will get it, this being the leftmost bit. I guess we'll get it from the 3rd bit position, for example. Multiplexing basically means that, right? Something like this. That's what you have to select into this multiplexer. In this case, you may have to pick the 1, that's like the 3rd into the 4th. And then into the 3rd, you have to get the 2nd into the, 1st, let's say, call it. You get this one maybe. And then you have to put a 0 here. Like that's a left shift, if you notice.
Right.
And this you have to select, basically. You will have, since you have 4 inputs, you have 2 select lines. And you can program these, for like select. If you put 0, 0, you may just do this. If you put 0, 1, right? In other words, not 0, 0. In this case, actually, like you have to put here, if you want to do this, you have to put 1, 0 or something. So you can design, and like these are the 4 bits ultimately that'll just develop. You can write a nice logic, table. I mean, you learn these things in ENEE350. I don't want to be too explicit about it, but this is a multiplexer design. Multiplexers are universal networks, as you probably learned this in ENEE350. You can design anything with them. These are basically and or blocks, right? What is a multiplexer?
Right.
Bunch of AND gates followed by an OR gate. That's like an AND OR circuit, and you learned in canonical forms, what these sum of products are, and that's why these are universal networks. A decoder with an OR gate is a universal network. You can also design it that way. Lots of different ways you can create these shifts if you want. These are called typically barrel shifters in ALU speak or computer architecture. I don't know if I asked all these things to you. I'm not sure, but maybe I did, maybe I didn't. What you need to do, I think, is to go carefully. Maybe I did say, do this one. I can actually take a look at the, let me just take a quick look at the problem. I have it right here. I can tell you if I asked you about this or not. Okay. Go ahead.
I don't think you did.
Oh, okay. I'm just looking at the first assignment here. What is it?
So this,
Yeah.
where I got the shift left or shift right by 1 bit was from C that should be D, the second C.
Yeah. So it seems to me that I didn't actually ask.
Right.
Yeah, I didn't. What I see here is that I only ask you to design. Well, actually, I did. I did in G. Yeah, I did. Maybe yeah, I should say I did. So it says show the design of a typical flip-flop in register A.
Right.
Just like when we did this sum, I showed you like, what did I do? I wrote, maybe you said, mathematical equations. Okay, so maybe that's what you're saying. Like in the add instruction, if you recall, what we did, we said, okay, sum bit SI is equal to like AI exclusive or BI exclusive or CI, where CI is equal to GI plus PI times, GI plus PI times CI. where GI and PI are generator and generate and then propagate carries. I must have written those down. In other words, I did write the logical expressions. I didn't, show you an actual ripple adder or some other adder. Okay, or look ahead adder in this case. So maybe that'll suffice. I don't think you'll have to actually show the shift circuit, but you may just want to say, here is what I would take, like that A left arrow 1 1 goes straight into, but you have to pick a particular bit of that. Remember, I talked about a typical flip flop, and it's also what G is saying. Do a typical flip flop. So you have this OR gate that goes into the input of this typical flip flop, right?
Right.
And you have to figure out now at what time you put whatever result in there. You
Right.
got these 18 instructions. Every one of them will have something to go in. Maybe not every one of them. Some of them will impact A. Like I can see, for example, decrement will decrement A. That means something will change in A. Sub will definitely change A. Complement will change. OR will change. AND will change. XOR will change. Those things will all change A. So you have to have a
Right.
big OR gate in front of that thing, right? Are you
Right.
picturing this? Like, you're going to have a big OR gate, right?
Right.
Big OR gate in front of that typical, big, huge OR gate in front of this typical flip-flop of A, Q typical, let's say, or QI, whatever. This is like A, A register, that is. And then you have to have these AND gates like this. Now, what are these AND gates for? So you're going to push in, either AI here, or complement of AI, or maybe shifted value of AI, right? You have to write the right notation. I'm just, writing a rough thing here. Like, okay, so every one of them has to happen with some state that you're in. These actually will be, like decoder outputs. You're going to have, I think, 19 instructions. So I'm in 18.
Yeah,
You need
there's
5 bits, 32 outputs.
Yeah.
So you need this 5 by 32 decoder here. These outputs will actually go into these places, etc. Okay. Right?
right.
I'm not drawing this properly. I'm just giving you an idea. Okay.
Yeah.
But this is the idea. And that's how you're going to do that typical QI. Are
Okay.
we done?
I guess my last question would be, for clear, are you just setting everything to 0, or?
Clear means like clear A means everything becomes 0.
Okay, thank you.
In A, yes. In A, that is not anywhere else. All right. Well, thank you, Maria. I'll see you on Thursday.
Yes, thank you so much.
Oh, you're welcome. Take care.